so I should be recording now. All right, so the kinematic equations, that should be an I, that we've looked at so far, we said that v final equals, so the final velocity is equal to the initial velocity plus acceleration, and I'm just going to write it as t, like we're making the assumption, oh, I should, for these problems, I should actually write it as delta t, just for these problems. You'll see why in just a minute. So this is like, sometimes we call this the first kinematic equation, but the next two equations, we don't really say the second or the third. So I think the other one that I showed you was, did I say it was like, yeah, so I think we'll call this delta x displacement for now. The initial velocity times delta t plus 1/2 a delta t squared. We're going to look at another kinematic equation, not today. So today, for these problems, we want to use this equation right here. And I'm just trying to, I don't know, like, let's try to get this. Okay, here they are. So for this one, I'm going to share this other screen with you. So for number one, it says, what is the final velocity of a car after 5 seconds of accelerating from rest at a rate of 1.5 meters per second squared? So just different color. So when I solve these problems, or like when I teach people how to solve them, the thing we're looking for is the final velocity. We know what the initial velocity is. We know what the acceleration is. And we also know what the time is. So what was the initial velocity? It says acceleration from rest. Was that initial velocity? Very good. So it starts from rest. And what's the acceleration?
1.5 meter per second squared.
Very good. And how long is it accelerating for?
5 seconds.
5 seconds. Very good. So I always start with the equation that I'm working with. I know that it's going to be v final plus a. We actually could use just t for now. So in this case, v final, v initial, this is 0. So it's going to be acceleration times time. Did anyone get that as a number?
Yeah, I think it's 7.5.
Yep.
7.5. What are my units on that?
Meters per second.
Very good, meters per second.
Yeah.
And I'm just going to kind of highlight that because like this unit of second squared cancels this unit of seconds. So you're going to get meters per second. It's always good to check to make sure sorry, I'm just looking at, where is it? There you go. It always is good to make sure that you have the correct units after you multiply this out. Now, a few things that I did want to kind of point out. This first problem didn't really tell you what direction that the car was accelerating. It just said a car is accelerating from rest. So it didn't tell us the direction. Didn't say whether it was positive velocity or negative velocity, but we made the assumption, which is okay for this problem. The thing that it did say is, and let me go back, let me switch screens here. Can you guys see that I put the acceleration problems back up? Is that,
Yep.
You guys can see this? Okay. Now, in this case, you see how for this, it said like the accelerating at a rate of 1.5 meters per second. So since you're starting from rest, all right, so your initial velocity is 0, and it's giving you, in this case, didn't mean to do that. And in this case, it's giving you like a positive acceleration. Sorry, is someone trying to come in the room? Okay, I think everyone's in. So in this case, if they're telling you the acceleration is positive, and you're speeding up, the velocity should be in the same direction. There is one that I would like to look at. It's always good to draw the acceleration in the velocity vector. So let's take a look at, yeah, let's take a look at number 2 together.
Normally when we
Oh,
draw
say
the
it again.
vectors, should we draw the vectors before or after we finish solving the problem?
Yeah, normally it's good to do it before because, and that's why I'm going to show you this one. So if we look at number 2 together, it says, what is the final velocity of a car after 3 seconds if it is slowing down at a rate of 2 meters per second and has an initial velocity of 21? So first, what I would like to do, so this would be like number 2. And can you guys help me summarize that information? So I think I said we're looking for the final velocity again. So I'm going to write this equals a question mark. Now the thing that I did give you, so the initial velocity, was it 21 meters per second? Is that what it was?
Yeah.
Now, in this case, I call it 21 meters per second. Which direction? So like if I'm drawing a velocity vector, and this is going to be velocity, should it point this direction or should it point this direction? Like call this the
right.
positive. Yeah, it should. Oh, I don't know why I did 2 negative or 2 positives there.
To the left, to the left.
All the velocity
Sorry.
vectors to the left. It's all good. It's all good. Yeah, so like for this one, now this is slowing down, right? So what was our rule when something was slowing down for the acceleration vector?
It has to
Do you
be opposite the.
Yeah, so
This.
yeah. Yeah, keep going. Yeah,
Yeah,
Jen, you had it
no.
right.
So it's supposed to be pointing in the opposite direction to the velocity vector.
Very good. And so in this problem, here's the tricky part. They use this word slowing down. So that word that said slowing down, it needs to make you think, oh, I have to be careful about what the signs are on velocity and acceleration. So if you look in this problem, I gave it to you as 2 meters per second squared. And I told you the direction though. I said slowing down. So when we
So-
go to fill in our numbers, what should we plug in here? Like, so was that 2 meters per second squared, but what did I not include?
Yeah.
Yeah, so like you have to be very careful, all right? And you have to include the negative. So I don't want to write slowing down, but we know this, right? So like from our vectors, I don't want to write our vectors, but from the velocity, and that's supposed to be an and, acceleration vector, we know it's slowing down. So we have to change the sign ourselves. So include the correct sign, positive or negative. So we have to go and put that in ourselves. So be very careful about that. Now there's one other way to know that. If you were to use let me put one last variable. We said what, delta t was 3 seconds?
Yeah.
So like if you put, so first let's do this correctly. So like let's first just use our information. We know V final is V initial plus A delta t. Our initial velocity is what, 21 meters per second plus, we know it's a negative acceleration minus 2 meters per second squared and 3 seconds. Okay. So from this number right here, -2 times -3 should be
6.
negative, very good, -6 meters per second. All right, so 21 minus 6 should be, I believe, 15 meters. Now, here's the trick. If you put, like, if you were like, I'm just going to plug in the numbers I know, and let's say instead you wrote plus 6 meters per second, you know, because like you didn't include the negative sign. would this thing have sped up, increased in velocity, or decreased in velocity? Which of those two would happen? Yeah, so like if you were to use that calculation and forget what sign it was, whether it was positive or negative, if it's now going faster after 3 seconds of slowing down, you made a mistake. So like, don't just use these formulas and by plugging in information. Be careful of the sign of the vectors. Okay, be careful of like, you have to just like go to the next step and think about what's actually happening. Okay, if you guys could, let me give you one. Let's look at one more problem. I'm going to have you guys do it. So. Would you look at number 5? Yeah, number 5. Try doing number 5, okay? And then we'll do it together. What was the initial velocity?
Negative 4.5 meters per second.
Very good, negative 4.5 meters per second. And we're looking for the final velocity, question mark. And at what rate is it slowing down? How fast is it slowing down? What's our acceleration?
1.5 meters per second squared.
Negative.
Very
Is
good.
it negative?
Yeah.
No, in this case, so like this is why I included this one. So our initial velocity is in the negative direction. Okay, so that's what, and for this one, I told you like velocity is like negative 4.5. So like, oh, right away when I do that, when I think of that, I automatically go in and draw my velocity vector. So I know it's moving in the negative direction. Okay, so it's kind of like I guess like in our coordinate system, like if you want to think of a coordinate system where this is the positive x direction and this is like, this would be positive y, kind of like our Cartesian coordinate from math class. Anything with a negative velocity is moving in this direction. So this is like negative x, negative velocity. So we don't have to change the sign of the acceleration because I'm going to use the velocity vector to write a acceleration vector. And in this case, the acceleration vector, it's pointing in the positive direction. The important thing to know about this, although this vector points in the positive direction, don't think of the acceleration as pointing in an actual physical direction. It's pointing in the direction the velocity changes. Okay, so just be careful about interpreting that. What was the time change on this one? How long did it take? 2 seconds? Now, let me ask you guys a question. So I'm going to draw a number line. Let me do this right here. So like,
Yeah.
if you will think of like, what were you saying, Matai?
Shouldn't it be -2 seconds because it's slowing down?
No, time will always be positive. So time,
Actually, yeah.
always positive.
Yeah, that's true.
No, it's a good question because like, and that's why I'm drawing this next axis. So if you think about this as, so if this is like a velocity axis, not like a distance, but like, imagine, so so this is what, like, let's call this minus 4.5 meters per second. And we'll call this plus 4.5 meters per second. Now it says, what do we say, slowing down? So if this is slowing down, after doing this calculation, would you expect a number like, oh, sorry, meant to change that color. Would you expect the velocity to be something over here? Or do you expect the velocity to be something over here if it's slowing down? What do you think? So if this is slowing down, should this number be going closer to 0? Should it be going this way, closer to 0? Or should it be getting bigger, going in the opposite direction of 0?
It should be closer to 0.
Very good. And it's important to make that connection before you start plugging numbers in. That way you're making a prediction, right? You're trying to predict, is the number going to be bigger or smaller? So in this case, when I say smaller, it's going to be closer to 0. Okay. All right. So now now we can plug in our information. So we have, let me just go here. So we have V final, the final velocity, equals the initial plus our acceleration, and guess I'm writing delta t. So again, we'll put negative 4.5 meters per second, plus our acceleration is 1.5. We're slowing down, but we still call it acceleration. The English language is terrible because we have a word acceleration to mean in English speeding up. Also in the English language is another word called deceleration, which always means to slow down. I oftentimes in physics only use acceleration, and I mean it for both cases, speeding up, slowing down, and we have to look at the sign ourselves. Like, so I know that 1.5 times 2, this should be like 3 meters per second. Excuse me. And I'm good for this problem, just to kind of show it. You don't have to do this step out. I just wanted to show this side by side. You have like, oops, sorry, that should be 4. Thank you. So this one should be, let me erase that, make it easier to see. This one should be 4.5 meters per second. So just to show you, like the velocity is decreasing by adding a positive number. So I think this should be a 1.5 minus 1.5 meters per second. And so like, maybe that's what this value is up here on our graph. That airplane is incredibly loud. So this would be like, our negative 1.5 meters per second. It's slowing down. It's getting closer to 0 in this case. All right. Any questions on this?
Yes, I have one question. Would it be
Yeah.
technically wrong if you would do negative 1.5 times -2?
Negative 1.5. Yeah, because time will always be positive. So like that's an important point to bring up. Time delta t is always positive. If you think of it this way, like, and you guys are bringing up good questions. So, right. So if we had a graph of something, right? So if I had a graph and this is our time axis, and this is like, like for now, if we wanted to say velocity, right? So if I said this is just velocity here, okay. And I were to draw a graph of like a car accelerating, maybe it looks like, for just so that we don't say its initial velocity 0. So like maybe it looks like that. Now we know that right here is t equals 0. We start our stopwatch. We like, okay, we have our stopwatch and we're like start. And so like we started at time t equals 0. We know that, the car is sitting at like, the starting point before that, but anything before that t equals 0, we don't know what's happening, like at least not for our experiment, right? Sometimes like we like to joke like this means like you travel back in time, or we just say backwards time travel. And at least in the physics that we'll talk about, backwards time travel does not exist. So there's a very famous law of physics called, I always confuse them. I want to say it's like, I want to say the third law of thermodynamics. So thermodynamic, I always confuse them because there's like a 0, a second, and a third law. A 0, first, second, and third law. Dynamics. We'll just say laws of thermodynamics says you can't travel back in time.
That technically is kind of wrong, no?
In what way?
Like, I'm not sure about what I'm saying, but it's like if you're in a plane and you're like going faster, I forgot, if like you're going
If you go in another
faster,
time zone and
Yeah, so-
you're 1 hour late, or yeah.
or like a few seconds. Wait, I heard this somewhere, but it's like if you're traveling at a certain altitude, I think, or like something, then you
So I
like
think what you're referring to, so like I think you're referring to something called the twin paradox. And hang on one second. Let me just find you a picture. Where's my? Can you guys see that I'm opening up just Google?
Yes.
Can you? Okay. There was something very famous called, and this is where like Einstein became very famous. He had something called the twin paradox, and let's see if we can find just a good pic. Oop, I don't know what just happened. Another window open. Okay, I just wanted to look at pictures. Let's see if they have a.
excuse me, I think I found it. So it's like if you're traveling closer to the speed of light, time slows down for you.
Correct. So like absolutely. So what you said is absolutely true, and that's what he said. Oop! I keep hitting like a button, and another window opens. So the faster you travel, so the closer to the speed of light, which is the universe's kind of speed limit as we at least know about, or at least to the extent that we can prove it, the universe seems to have a speed limit. You can't travel faster than light according to Einstein's theory of relativity. And we'll talk about this more in, I think, DP physics too. Time slows down, but it doesn't go backwards, if that makes sense. So like you'll often see like this, like a picture like this, you have a person here on Earth, and then you have a person traveling away from them, like this is called a thought experiment, traveling away from them close to the speed of light. And what happens is if you have two clocks, one here on Earth and one on the spaceship, and they're synchronized, right? So like, let's say at, what time is it right now? Let's say at noon today, we have two watches, two clocks, we synchronize them and we hit start at the same time. they have the exact same time. Well, in theory, if this person speeds away from the Earth at the speed of light, and they return in like one of their years, so they're looking at their clock, and after 1 year they return back to Earth, then the person who's here on Earth will have actually aged. They will have grown older, whereas the person who is on the spaceship will have only appeared to have aged 1 year. All right, I'm gonna do stop screen share just so I can see everyone. Who has seen the movie Interstellar? Who's seen the movie Interstellar? So there's this scene in that movie. So hang on one second. Let me share my screen again.
Oh, yeah, that scene is really sad.
Yeah, like so the guy got stuck, like literally. So like, hang on, why is it not sharing? Let me see if I can find it on YouTube really quick for those who
Wasn't he
didn't see
like
it.
there for like 10 years or something?
Well,
Or-
I think when like the astronauts, whatever we'll call them, when they went down onto that planet, hang on, let's see, there we go. Another way, besides traveling at the speed of light, if you go into a super, like, for lack of a better, I don't want to be super precise with my words, but if you were to go into a very strong gravitational field, like you can also alter the rate at which time passes. And we use this word relative to each other. So hang on, interstellar. What would you call that scene? Oh, black hole. No, it wouldn't be the black hole scene.
No, it's like the
Planet
ocean.
landing.
Yeah, maybe ocean planet landing or something. Maybe.
Let's see if it comes up as this.
Yeah, that's the scene.
Oh wait, I want to try one other thing. So return to shift. Yeah, this scene.
Oh yeah,
I
that.
think it's this
Oh
one.
my goodness.
So I don't know if you guys can hear it at all. Let's see. It's just playing music right
So the
now.
lost communications came through.
How?
The relay on this side
Uh,
cached them. So years of basic data, no real surprises. Miller's side has kept pinging thumbs up, as has Dr. Mann's. Edmonds went down 3 years ago.
Transmitters in here.
Maybe.
No, this doesn't. This is
Miller
not
still
the
looks
right
good.
one. Yeah, so he's like a young guy there, but hang on a second. You know, I'm gonna try one other one. Time dilation. There we go. Time dilation scene. Figured that would be it. I'm gonna speed it up. We're not gonna watch the whole thing, but like, let me find the spot. So basically, where to go? So they're gonna get off this planet. The planet is very dense. And what happens is their time passes much slower than that. So I'm going to really mute that so we don't have to hear it. But when they return to the spaceship, let's see, kind of go forward. Okay, that's, yeah, all right. All right, so check it out. I'll try to find it, but maybe you guys could go home and Google it as well. So it's called time dilation. And what's really cool is we actually have experimental evidence that shows that, at least for atomic particles, that this is true. We actually have a lot of evidence, but we don't have the evidence for biological organisms slowing down. But everything that all of our experiments have confirmed that Einstein was correct, which is interesting. There was one other thing I wanted to add to that. Time dilation. Yeah, sorry. I don't know. I was going to add something, but I kind of forgot what I wanted to say. Does that sort of make sense? Like, I guess it does. Like, as far as we know, Einstein was actually correct, but what do we have? 8 minutes. Oh, there's there's one more problem that I would like to do today, and it's just I want to work. So I think I already deleted the slide, but so this is just the first kinematic equation. For homework, would you just finish those problems? And then like, I just wanted to do one problem with you, one more new problem with you before we end class. We said that our kinematic equation, so we wrote this equation, V final equals V initial plus A delta T. You know, we'll call that like the first kinematic equation. It's really just acceleration, the definition of acceleration rearranged. But then we wrote like, we'll write delta X for now. The displacement equals initial velocity. And I'm just going to write this as T time plus 1/2 a t squared. And actually for this one, I'm going to do a problem in the XY direction. So in the Y direction. Like I want to figure out how far something falls after falling for, just a few seconds. What I'd like to do is imagine like you're standing on top of a very tall building. Well, I'm just not very good at drawing anymore, at least not with this. So you're on top of a very tall building. Here you are. And you're going to drop something. I don't know. Let's call it like, we'll just be like this thing here. And you're just going to drop it. We're going to talk a lot more about how gravity speeds up falling objects. But the acceleration due to the force of gravity. So Earth, we're here on Earth. And when you let something go, the moment your hand opens, the gravity starts to speed it up. All right. And we'll talk about where this number comes from. But the acceleration due to gravity is on Earth, we say minus 9.8 meters per second squared. And this is actually constant acceleration. We'll talk a lot more about this because it's actually really important. But on Earth, things speed up at the exact same rate. Okay. I feel like I'm really trying to rush this. We'll try to do it. What I'd like to do is we're going to release this from rest. All right. So let's say V initial equals 0. All right. We're just going to we have something in our hand like a ball, and we're just going to drop it. And we're going to see how far it goes after what do you say? Like, let's say 2 seconds. All right. So we'll release this from rest. Release from rest. So we're just going to drop it. And this will be our last problem for today. What we want to do is how far will it fall? Okay, so we're going to just start with this equation. And we're using delta y in this case because it's the up and down direction, which we call just delta y. And we're just going to do V initial times T. Oh, how far will it fall after 2 seconds? I should write that after 2 seconds. Plus 1/2 a t squared. And one of the things that you're going to see some shorthand notation here. I know that the initial velocity is 0. Why? I'm dropping it or releasing it from rest. So this whole thing should be just 0. So I usually just like put this little cross through that term and point to a little 0. Okay. And that just means like this term is 0. So now this is just going to equal 1/2 of the acceleration, which in this case, gravity is just 9.8 in the negative direction, 9.8 meters per second squared. And I'm just like telling you after falling for 2 seconds. Okay. Now, just to look at our units. Sorry, I made one mistake. Right. 2 seconds squared. Okay. Because like this term right here is a t squared.
I have a question.
Yeah, go ahead, Jen.
Is it only the t that is? Yeah, it's me. Is it only the t that is squared?
Correct. Just the t term.
Okay.
I'm just going to write this extra step out, like 9.8 meters per second squared. And this is going to be like 2 seconds squared. So this should actually be 4 seconds squared like that. All right, so we're squaring both the number here. Sorry, number here. We're squaring both the 2 and the units, because the units of seconds will cancel out. Second squared cancels out. And the number, I think, if you do this in your calculator, it should be what, negative 19.6 meters. Okay.
Yeah.
And so, like, you know, just multiply these all out in your calculator and you should get negative 19.6 meters. Why negative? And the answer for that is, if we assume, like, you know, wherever we drop the ball from, it's going to go from here straight down. Well, should drop to here, negative 19.6 meters. So it's like moving in the negative direction. So like I did this problem really quickly. You don't have any homework problems with this equation. So the remainder of that sheet, so for this worksheet, I think you just have 3 more questions and they're all using the first kinematic equation. So like these are just the first kinematic equations. So do those problems for homework, okay? And then we'll talk about them on Thursday, okay, when we see each other in class. Does that make sense?
Okay. Yeah.
All right.
Yeah.
So check it out. You guys have a good day
Bye.
and I'll see you Thursday. Yep. Bye.
Bye.